These notes are on graphing trigonometric functions with transformations. So the first thing we're going to look at is the sort of standard form for sine functions with the standard form. The mother function for sine functions is y equals sine x. And then we add in a whole bunch of details, which I'm going to do in a variety of colors because it'll make it a little more exciting. We can multiply our function by something, sine. We can multiply our x by something, b. We can add or subtract something to our bx. And we can then, at the very end, add something to the entire function. So let's talk about what each of these things do. The a, we call this the amplitude. And the amplitude gives us our maximum, minimum height for our function from what we're going to just sort of for now call this 0. And it's sort of, you'll see when we're graphing this what I mean by this 0. We can also call this a vertical dilation, vertical stretch, and it changes our y values. So when we're looking at a table for this, what's going to be affected by the a is the y values, not the x values. Next, we have b. And the b is called the period of the function. And basically, it's the cycle. So for y equals sine x, a full cycle is from 0 to 2 pi. However, that can change. And so in order to get our period, we need to use the formula 2 pi over the absolute value of b. And this is a horizontal dilation, a horizontal stretch or pushing in. And this changes where, so the x, the function follows our 0, 1, 0, negative 1, 0 pattern. Our c is called the phase shift. And we get that by finding c over b. And this is what we call a translation, left or right. So this is just taking the original shape and moving it one direction or the other to the left and the right. And then d does that for our up and down. So we call this a translation up or down, and it changes our y values. Where this translation left and right are going to again change our x values. Change x values, as does our horizontal dilation. So now we're going to look at what all of that means, because it's pretty intense in terms of all the things that happens. So we're going to look at 4 functions. We're going to look at y equals sine x, y equals sine 2x, y equals sine 2x minus pi, And I'm going to have enough room. Nope, I'll put it on the next line. Y equals 3 sine 2x minus pi plus 1. And one of the reasons why I'm looking at all of these functions and that for now I'm kind of only adding a layer each time is because I want to see how each of these affects the previous function. So what I'm going to do is I'm going to make one huge table right now with all of these functions. And I'm going to start talking about the way in which the table changes depending upon what it is that how the function has been transformed. So I'm going to start with my, I'm going to start with the sine x, and I'm going to have x and y. And I know that one period in my sine x function goes from 0 to 2 pi. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I know from lots of experience doing these problems now that when sine is 0, when x is 0, sine is 0. When x is pi over 2, sine is 1, 0, negative 1, 0. So that's the pattern it always falls. Unless, of course, I've changed my amplitude or I have changed my translation up-down. So now I'm going to add another layer. I'm going to add the layer of sine 2x. Now the 2, remember, changes our period. So instead of our period being from 0 to 2 pi, I've got to actually use the number they gave me, 2 pi over the absolute value of b. And so I have that my period is going to equal 2 pi over b. But my b in this case is 2, which gives me a period of pi, which basically means that my x's, instead of going from 0 to pi to 2 pi, they're going to go from 0 to pi. That's one period this time. So instead of 0 to 2 pi, one period is going to be 0 to pi, one cycle. So then I have to break this up into equal portions, which is going to be pi over 4, pi over 2, and 3 pi over 4. Or 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. However, this doesn't change the values, my pattern. So this just smushes it closer in or expands it further out. And so my pattern is still, for my y's, 0, 1, 0, negative 1, 0. So let's start by graphing these two functions right next to each other. So I'm going to pick up another page because we obviously do not have room to graph this on this page. Let's see if I can pull this. Okay, so I'm going to say y equals sine x. And I'm going to say this is 1, this is negative 1, pi over 2, discounting, pi, 3 pi over 2, 2 pi. So I've got 0, 1, 0, negative 1, 0. And there's my lovely sine shape, one period. However, when I add the 2 in front, we can see that actually I'm going to be smushed into this interval. So I actually, for my y equals sine 2x, as long as I'm using the same scale, which is kind of nice to use, because then I can really see the smushing that's happening. That my pattern is going to be 0, 1, 0, negative 1, 0. So I've taken this function and actually smushed it horizontally. It's a dilation. It's smushed in. Okay, let's look at what happens now if I add another layer to my function. So let's say that I'm going to do sine 2x minus pi. So in this case, I already know that my period has changed. So I already know that I have my x's are already these. So they're already 0, pi over 4, pi over 2, 3 pi over 4, and pi. But the c does a phase shift. So the phase shift, I have to look at the c over b. So my c over b is c over b, which means that I have to move to the right pi over 2. So basically, I'm actually adding here pi over 2 to each of these values. And let me do one more column here. Let's have this still be x. So basically what I've done is I've taken my x's, and the first thing I did with my x's is I smushed them in, I got them closer, and then I took my x's and I translated them to the right by pi over 2. Remember, this sort of notation you've seen with parabolas, you've seen with absolute value, you've seen with logarithmic functions, that we're looking for what would make x be 0, and so it's c over b, which is positive. Okay, so now I add pi over 2 to each of these. Common denominator, that's going to be 3 pi over 4. That's pi, 5 pi over 4, and 3 pi over 2, or 6 pi over 4. And this, again, these values, the phase shift and the period, don't change my pattern of 0, 1, 0, negative 1, 0. So let's graph this function. So y equals sine 2x minus pi. So in this case, I actually have to extend my graph, my x's values further out. So over here, I just went out to pi or 2 pi. But in this case, I'm going to have to go all the way out to 3 pi over 2. Sorry, actually, I'm actually going to be sort of looking at a smaller portion. So we have pi over 2, pi, 3 pi over 2, and 2 pi. So it actually works out that basically I'm taking this picture right here, and instead of it being here to here, I'm moving it here to here. So my pi over 2 is 0, 1, 0. Whoops, I've messed this up on, so it's 1 here, 0 here, 1 here, and 0 here. So again, it's still got that smushed shape. It's simply that I have moved it over by pi over 2. The last function that I'm going to look at adds in the amplitude, the up-down shift, and adds in the the up-down translation. The amplitude changes the vertical dilation, and the D changes the up-down translation. So I have sine, we added in the 3 in the front, so 3 sine 2x minus pi plus 1. So if you remember, we talked about the fact that actually the amplitude and the number I add outside of the parentheses of the sine function, so I add at the end of the function, change my y's, which means I now can keep my x's exactly what the same as they've been. I have not, because these functions are all being built upon each other, this 2x minus y is what affects the x, and I already did that in the previous problem. So I have pi over 2, 3 pi over 4, pi, 5 pi over 4, and 3 pi over 2. So the amplitude tells me to take my original y's and multiply them all by 3. And then it tells me, my plus 1 tells me to take those values and add 1 to all of them. So I end up with 1, 4, 1, negative 2, and 1. So I now can do my last graph. My last graph is not going to fit on this paper since I actually, given the scale of my graph, so remember my scales here was that I did 2 boxes was 1, so in order to get up to 4, I'm going to have quite a bit of space. So we'll take these off for now. We'll put our table up here. And so then we have, just make sure, 4, 3, 2, 1, 0, negative 1, negative 2, and I need to go down to negative 2 is my lowest, so I don't need any more than that. Okay, so now again, I scale it the way I've been scaling, so pi over 2, pi, 3 pi over 2, and 2 pi. I already know that I start at pi over 2, and I'm going to stop at 3 pi over 2. So I already know I'm in this area. I also know that instead of being at 0 here, I'm going to be at 1. And then the next one, I'm going to be at 4, back down to 1, down to negative 2, and back up to 1. And so my graph looks like that. So at the beginning of these notes, I kind of talked about this idea of 0. We talked about the amplitude being the maximum height and minimum height from 0. So if we look at these 4 graphs, in our first 3 graphs, because we didn't change our up-down translation, our 0 was 0. However, when we changed our up-down translation, our new 0 became 1. That became the place where the function keeps going back to as that 0 value. So if we look at these 4 functions kind of in a row here, the 2 smushed us in, the pi moved us over, and then we had our stretch and moved up. And so that's what all of those numbers do. Now, the reason why I did this in this order, where I started with x, then the 2x, then the minus pi, then the 3, and the 1, is because that's what you're going to do whenever you get a function. So if you are going to get a function where it is, y equals negative 4 sine, parentheses 3x minus 2 pi, parentheses plus 4, you're going to have to start with whatever you're multiplying your x by, then whatever you're adding or subtracting to that x value, then whatever you're doing your amplitude, and then whatever you're doing your up-down translation. That is the order in which you perform the changes in the table.